So this is the expression for the linearized virtual work for the total Lagrangian principle, where we started from S and E, envisaging that our constitutive equation will be given in terms of the second peak stress and the Green Lagrange strain tensor. So um, in this, uh, one of the major tasks is the calculation of this fourth order tensor. Now, this fourth order tensor, as we have learned, is for our total Lagrangian case,Cijkl is equal to del Sij del Ekl. Uh, this depends, the form of this depends on the stress and strain measures, or the stress and strain rate measures that we have adopted. In this case, these are the strain and stress and strain measures that we have adopted. SoCijkl is del Sij del Ekl, and this in order to calculate this, we have to realize that for a hyperelastic problem, we have already found that Sij is uh, del psi 1 del Eij. So this follows from thermodynamics, and plugging it into this, we have del Kl of del psi 1 del Eij, which gives us del square psi 1 del Eij del Ekl asCijkl. So if we know the strain energy density function, then its second derivative with respect to the strain measures of our choice will give you theCijkl, or the tangent stiffness that we have to use in the Newton-Raphson procedure for this material. Okay, so let's do an example where we find this easy example, and then we will do a slightly more difficult example. Now, it is possible that S is given as, or psi is a function of C, in which case we will have to take the second derivatives with respect to Cij and Ckl, and we can easily show that this will then translate toCijkl is going to translate to this, and then S, remember Sij is 2 times, so this we have also derived from thermodynamics, plug that in here, and also this one Cmn is half Cmn minus delta Mn is equal to Emn. So 2 Emn plus delta Mn equal to Cmn. If you take the derivative now with respect to Ekl, so you will get 2 delta Mk delta NL, this goes to 0, equal to this, which appears here. So this is 2, so this would become del Sij del Cmn delta Mn delta NL, and 2 here, which would lead to 2 del Sij. M and N gets knocked off in sorry, this is MKNL, delta MKNL, so this would become CKL. Now Sij is twice of this, so you have 4 times del square psi naught del Cij del CKL. That's equal to yourCijkl, in which case In the case where Sij is a function of C and not E. So either way, we can use either this or this, and in either case, we'll have to take the second derivative of the strain energy density function given in terms of E or in terms of C uh, with respect to E or C. So that's what we have to do, and let's now do a problem where we try this out. So here's the problem where your strain energy density for a hyperelastic material, it's called as Venant-Kirchhoff material, is given in this form in terms of E. So to find Cij Mn, let's say, we will use del square psi 1 del Eij del Emn. So that's my tangent stiffness, and let us write this in terms of initial notation. So this will be equal to half lambda E, let's say kk square, that's trace of E square, plus mu times E pq EPQ, right? So first do del psi 1 del Eij, that will give you 2 ekk, so 2.5 cancels, so you have lambda delta ki delta kj, that's what you get from here, times ekk. That's from the first term. From the second term you get mu times delta pi delta qj into epq plus epq times the same thing, delta pi delta qj. So this becomes delta ij, this becomes eij, this becomes eij as well. So I'm finally left with lambda ekk delta ij plus 2 mu times eij. So that's the first derivative. When you take the second derivative, you have to do it in terms of Eij Emn now. When you do that, from the first term you get lambda delta ij, delta km delta kn plus 2 mu E im E delta im delta I delta jn, that's what you get. So this obviously becomes delta mn, so finally Cijmn becomes this. Now you would see that this has almost the same form as the elastic stiffness for the Saint Venant-Kirchhoff material, which is not surprising because this is a quadratic strain energy density function, so the derivative of that would be linear, and the second derivative of that would be a constant, which it is. However, this has symmetries with respect to ij. It has also got symmetries with respect to ij and mn. So some of the minor symmetries and major symmetries are satisfied, but you don't have a symmetry with respect to mn. So if you switch mn, this remains unchanged, but this becomes injm, and that symmetry is not present here. So that is because of the way we did this derivative of Eij with respect to Emn. So when we take the derivative of Eij with respect to Emn, we have to consider the fact that Eij del Eij del Eij del Emn is a fourth order tensor, and it's in fact it's a fourth order identity tensors, which will give us delta I m delta jn plus delta in delta jm and half of that. So this is the fourth order identity tensor which will result from here. We had only included this term and that's what is here. If we had included both these terms and written the correct fourth order identity tensor, this is also a fourth order tensor, but it's not the correct fourth order identity tensor, taking into account the fact that if you change I and j here and m and n here, if you switch them, the derivative remains the same. To enforce that fact, you will have to use the correct fourth order tensor. And if you do that, then you have all the symmetries of IJMN that you expect for the elastic stiffness. Okay. Well, a very important hyperelastic strain energy density function is what is given here. Is called the Neo-Hookean strain energy density function, and it is phrased in terms of the invariance of C. So I1 is a trace of C, the first invariant, and I3 is the third invariant of C, and J is J square is equal to I3. So with this, this is a strain energy density that is used quite widely in nonlinear elasticity, especially for very soft materials like biological materials and hydrogels and so on. So we will use this strain energy density function to go through the whole procedure of deriving the tangent stiffness matrix. So in this case, the tangent stiffness matrix, remember we have to, the tangent stiffness matrix that we are deriving is this. SoCijkl is this. In this case, it is phrased in terms of the invariance of C. So, sorry, this is EKL. This is what we are deriving. This is phrased in terms of C. So we will have to convert this into derivatives of C, which we have already shown. So we will use those tricks that we have learned in order to derive first the first pk stress from second pk stress from the strain energy density, and then taking the derivative of the second pk stress, we will derive the stiffnesses. So let us write this down. So psi hat is equal to mu by 2 Now to derive S, which is del psi hat del E. So this is S. We have derived this from thermodynamics before. We will have to do the following. We will have to use S. Sij is del psi hat del Eij, which is equal to del psi hat del Ckl and we have seen before that this Ckl, so EKL is equal to 2EKL is equal to CKL minus delta KL. So CKL is 2EKL plus delta KL. So del CKL by del E Ij is 2 times delta Ik delta JL. So I can replace this by 2 times delta Ik by delta JL, 2 times of that, and then I get 2 del psi hat del C Ij. So Sij is equal to 2 times del C del Ij. Now to derive this from here, we will make use of a result that we have learned earlier. So So let's go back to a result that we had derived earlier. So we had derived this result earlier where uh, where we had assumed that psi is a function of I1, I2, I3, and which are uh, which are themselves invariants of E. And then following that trend, we had for derived this expression for S, where C0, C1, and C2 are given by these quantities, which can be immediately derived if you have if you know psi hat. So taking psi hat to be the Neo-Hookean function, we will derive this C0, C1, C2. But while doing that, we have to remember the small change that has happened. I1 is no longer the invariance of invariance of E as it is in this case. They are invariance of C. So we will have to keep that in mind while deriving the new C0, C1, and C2 that will be applicable here. So let's do that. Now remember, we have derived that Sij is 2 times del psi hat del Cij, where psi hat is function of I1, I2, and I3, where I1, I2, I3 are invariants of C. So we will write it as 2 times del psi hat del I alpha into del I alpha plus del Cij, and then we will have to calculate del I1 del C. This we have already seen. The first invariant with respect to the tensor itself gives you identity. Del I2 del C, we have seen this in case of E. This gives you I1 times identity minus C, and del I3 del C would give you I3 times C inverse. We had derived these expressions for the case of E, but they are valid for any symmetric second order tensor, and we have just translated them from E to C. So now if I plug it into the expression for S, I have S equal to 2 times um, del psi hat del I1 times I, so that is del I1 del C, plus del psi hat del I2 times I1. So this is what we'll get, and then again we can write it down in the same way that we wrote the one for E. We can write it down as we can take the I terms together, 2 times del psi hat del I1 plus here's a I term plus I1 times del psi hat del I2 times I. Then let's take the C terms. There's only one C term, so there's minus del psi hat del I2 C, and there's a C inverse term which is plus I3 . So this now becomes your, so there's a 2 here as well and a 2 here as well. So this now becomes your C0, this is C1, and this is C2. So let us calculate these derivatives. So we have del psi hat del I1 is equal to simply mu by 2. There is no dependence on I2. So del psi hat del I2 is 0. And del psi hat del I3 is equal to minus mu by j del j by del I3 plus lambda log j del j by del I3 Again, del j by del I3, j is equal to root I3 is equal to 2 root I3, that is 1 by 2j. Plug that in. So you will get minus mu by j square, 2j square, plus uh, lambda by, oh sorry, I missed a 1 by j here. So log j, 2 log j, 1 by j del I3, that's the correct derivative. So you have again 2j square here times log j, which leads to 1 by 2j square uh, lambda log j minus mu. So this is del psi hat del I3. So putting it all together, the second peak stress turns out to be mu times I minus C inverse plus lambda log J C inverse. And if you remember, the tangent stiffness is 2 times del S del C. We have derived this. Now, to do this del S del C from this expression, we need to know del C of log J, which will appear because of this term, and then we need to also know del C of C inverse. C inverse appears here and here, so we need to know this. So we'll come to this a little later. Uh, let us deal with this first. So remember that del I3 del C is equal to I3 C inverse, and then uh, I3 is equal to j square, so this gives you 2j del j del C is I3 C inverse, and del C of log j is 1 by j del j del C. We can take del j del C from here, so this would be I 1 by j times I3 by 2j C inverse, and then I3 is j square, so j square cancels, so this turns out to be half C inverse. So this is a result that we have to remember. This is equal to half C inverse. Let us now look at the other quantity, which is del C of C inverse. Now we want to look at del C of C inverse. And to do that, we start from the fact that del C of C inverse is equal to 0. So we start from this identity. So we can write del C PQ times C IK C inverse Kj is equal to 0. And taking the derivative, we have del C IK del C PQ times C Kj inverse plus Cik del Ckj inverse by del Cpq is equal to 0, and this is what we want to find, so we can take it to the other side and write it as equal to minus of this. This, remember, leads to the fourth order identity tensor, so this leads to half delta Ip delta Kq plus delta IQ delta Kp Ckj inverse is equal to minus Cik Ckj inverse times Cpq. So now to isolate this quantity that we want, we multiply this by, let's say, Cmi inverse. So when I do that, this becomes, so I have to do it both sides, Cmi inverse. So when I do that, this becomes a delta mk, and delta mk knocks this off, so this becomes del C mj inverse by del cpq. So this is what it becomes, and let's look at what happens to this. So this will become this side will become half of CMI, and this is IP. So this becomes C inverse uh, MP, and this KQ becomes QJ plus then MI, this becomes C MQ inverse and C JP inverse, that is equal to your CMJ inverse by CPQ. So we call this tensor, we give this a name. This is equal to I. This is a fourth order tensor which gives you del C inverse by del C. So this is equal to this new tensor that we have derived, which is I, and that's written in this manner. Now we have everything to derive the tangent stiffness. We start from S equal to mu times I C inverse plus lambda log J C inverse. So we have to calculate 2 del S del C. So let's calculate del S del C. That would lead to minus mu del C inverse del C plus lambda del C of log J times C inverse plus lambda log J del C inverse del C. These quantities are I that we have derived, and this quantity is half C inverse. So here this is a fourth order tensor, and this term needs to be handled a little carefully. So these terms are fourth order tensors. These are fourth order tensors. So this also has to be a fourth order tensor, and to realize how to determine how to handle this, let me just write this term. So what we are getting is uh, we are getting del Sij, let's say del CKL, which is CIJKL. This is what we are getting, and here this first term would be minus mu IJKL. The last term would be plus lambda log J uh, IJKL, and this should be lambda times half C inverse Ij C inverse KL. And now this has to be written as, this can be written as in bold notation as C inverse dyadic C inverse. So that leads to a fourth order tensor. So in the end, C will be uh, lambda log J minus mu times I plus lambda C inverse dyadic C inverse, lambda by 2, I think, lambda by 2 C inverse dyadic C inverse. So this is the tangent stiffness for the Neo-Hookean material. Now recall that in our linearized variational principle, we had the material stiffness term which contained ds, which we wrote as C times dE, with the understanding that we are calculating ds in the direction of triangle u, which was equal to C times dE in the direction of triangle u. We are dropping the triangle u here, and we have already found this. This is lambda C inverse dyadic C inverse plus 2 times mu minus log J I. This 2 comes because we have calculated del S del C, but we are supposed to calculate del S del E. So del S del E and del S del C are related by the factor of 2. That's why this change happens. Please do it yourself. So this times dE would give you ds, which then directly goes into the uh, material stiffness, calculation of the material stiffness. So next, once we have this all in place, once we have the tangent stiffness in place, the exact form of the tangent stiffness, the correct form of the tangent stiffness is very important, because if the tangent stiffness is incorrect, then it's not consistent, then your Newton-Raphson may not work. Newton-Raphson depends on a correct calculation of the tangent stiffness. So correctly calculating the tangent stiffness for your given strain energy density function is extremely important in nonlinear elasticity problems. And we have done that for the Neo-Hookean material. Now we will see how, once we have put all this together, how to discretize it, how to set up the finite element equations, that finite element equations for each and every element that will then be assembled and solved through the Newton-Raphson scheme.